And one of the variants of logistical regression that I've walked you through is a multinomial logistic regression. Of course, multinomial logistic regression will be on the final. So, uh, but today we want to go into another variant of logistical regression, or that we call or Poisson or regression. So, when do we use Poisson regression? When the response variable is a count. Okay, you know what determine the type of regression is actually the nature of response variable. I'm going to say that again. What determine regression type that we're actually going to fit is the nature of the response. When the response variable is continuous, we normally specify normal regression or linear regression provided as option old. When the response variable is categorical, and if you only have two categories, we normally specify binary logistic regression. Situation where the response variable is categorical, but we have more than two categories and they are not ordered. We use a multinomial logistic regression. And situation where we got more than two categories and they are ordered, we use a ordinal logistic regression. But right now, we got situation where the response variable is a count. An example of a count is the number of persons unalive by male or all skills in the Prussian army per year. It could be the number of people in line in front of you at a grocery store. When you arrive at a grocery store, of course, you see a lot of customers ahead of you being attended to. Okay, what determine, that is what we mean by a count. Okay, so what we want to do in the Poisson regression is can we actually identify some predator variables that are connected to the account, and that's why we want to consider Poisson regression. So another example here is the number of award earned by students at one high school. Okay, the number of award is not continuous. The numbers of award is not categorical. The numbers of award is a count. Okay, now if you uh, so the predictor of the number of award hand include the type of program in which the student was enrolled. So maybe you actually want to figure out what actually determine the number of award. So because the numbers of award is a count, so we're actually going to fit Poisson regression model. But you know what? Whatever we want to do in statistics, we normal so we if we want to model relationship, we normally start by specifying our model. Okay, I mean model specification. Model specification is very, very important. Now I want to walk you through Poisson regression or model and what each term in the model actually represent. Of course, I remember the other time when I was deriving the link function for Poisson regression, we derive log lambda, the logarithm of lambda. Okay, so and the lambda is the mean of a Poisson distribution from statistical theory. So, and that's why you're seeing expected value of y here. Okay, so the log expected value of yij equal the log of lambda ij. So what we want to do is we actually want to split the lambda ij into different components because the components are multiplicative, and that's why you are having the additive logarithm. So initially, what we have here is more or less like a lambda ij. Let me write what we have initially. What we have initially is actually, so what we have initially is like lambda. ij, okay, equal lambda, okay, lambda alpha I and the yij. That was why we have initially, okay. That was like a multiplicative, but introducing a log. We have that, no log of that. We're gonna have that. So how can we interpret each of these? So alpha is the rate ratio, okay. Yj is the rate or ratio, the effect of being in column J compared to the baseline, and of course, and so on like that. So, but you know what? I quickly want to walk you through example. For instance, if I want to model uh, the number of customers visiting a store from region in relation to some predictor. Predictor like number of housing units in the region, average household income, the average housing units in age, and of course the distance to the nearest competitor, and of course the average distance to stores in miles. Okay, we want to look at the effect of five predators on a response. But the response here is a count, and of course the appropriate regression type model is going to be a Poisson regression. Now, the very first thing is let's write the model down. Okay, this is the model. Can you see that? That is the model. If I ask a question like this in exam, and maybe I ask you to write the mean or the estimated mean function, or if you write instead of log lambda high, if you write maybe here, you write y, then you are no longer talking about Poisson regression model, but you're talking about conventional multiple linear regression model, and that is wrong. Okay, so you're actually going to have a log lambda high. Okay, now let me tell you this. This is the systematic part of a model. A model, we have both systematic parts and the error parts. Okay, we are assuming now that the underlying distribution of a random variable y given the predictor is actually follow Poisson distribution. Because why do we say it follow Poisson distribution? Because the response variable here is a count. Okay, so whenever a response variable is a count, then the distribution for the response is actually Poisson. Now, I want to show you the data. Okay, we have, this is the first 9 in the data. Don't forget, uh, we're talking about 110 region. Okay, if you look at here, can you see that? We have 110 observations. Okay, but I'm only showing you the first 9 here. Okay, I'm only showing you that. Now let's look at the how we do this in R. Okay, if you want to run this in R, okay, you actually still going to have a GLM because a Poisson distribution is a family, it's a member of a generalized linear model. Okay, when I talk about binary logistic, when I talk about multinomial logistic, when I talk about ordinal logistic, when I talk about Poisson regression, when I talk about beta regression, all of them, they are member of a generalized linear model. And that is why, all of these are actually called the variants of logistical regression. Now you can see what we have. Now, when you take a look at what I have, let me tell you this. I need you to pay attention now because by the time you are interpreting in exam, okay, when you are dealing with a logistic regression, binary logistic regression, or you are dealing with a multinomial logistic regression, okay, the link function is log, is the logit, is the logod, and all the estimates in them will be called a log odd estimate. I'm going to say this again because it's very, very crucial. Can everyone hear me? Everyone hearing me? Okay, this is very vital information. when I'm dealing with the binary logistic, or I'm dealing with the multinomial. Okay, the estimate that I got, they are on log odd. They call log odd estimates. Okay, if I want to have a meaningful interpretation, I'm actually going to do the exponentiation. Okay, when I do the exponentiation, I'm actually going to be talking about odd ratio. Okay, but in the case of a Poisson regression, we don't talk about log odd because the link function is log lambda and not log odd. Therefore, all of these guys here, they are on a logarithmic scale. Okay. Now, because of that, I need you to pay attention. I want to use a combination of these. I want to provide a mean function. To provide a mean function, okay, this is it. Take a look at this. If I were you in the exam, okay, not only in the exam, when you are doing your research, okay, now it's better to always tell the world which model am I using. That is the model. Okay, but according to this data, this is what I have. You can see now, I actually moved from statistical model, okay, back into a specific, because right now I actually telling the world what my X1 stand for. My X1 is housing. Can you see that? My X2 is income, and so on like that. Okay, this is according to this data set. Okay, but the general model is the one with x1, x2 up to x5. Okay, now, and you can see I wrote log lambda high. If I, instead of writing log lambda high, if I just write y, then I'm wrong. Does that make sense? So you got to be careful. Okay, now we have a model in place. How do we interpret? And I need you to pay attention now on how we interpret. So take a look at this. If I want to interpret a beta naught, okay, don't forget, I said they are on the logarithmic rate. Now, the 2.94 here, the 2.94, okay, here, and the one we approximate here, okay, I want to interpret that, okay, that's what I'm saying here. I need you to pay attention to this, okay. If you want to interpret, okay, do not let your interpretation to be statistically ambiguous. You don't scare. This will happen. Maybe you were consulted by a client. The client is seeking statistical guidance from you. And how do you present the interpretation to the client in a way that the client will understand? You don't want to overwhelm the client statistically or using your statistical terminologies. What are we going to say? Take a look at that. We said we want to interpret beta naught now. Said this is the baseline log expected count or log rate in the group with all covariates. Of course, you know how we interpret the intercept or covariate equal to 0. Okay, and that's what we mean. Okay, and you know what? Even though the interpretation here is nonsensical, for how can we have situation? How can we have a region where there's no housing, no income, no, everything is 0? Okay, so that is what that guy is trying to talk about. So you're gonna measure log rates. This is not rate. This is logarithm of rates. If you want to remove the log, please pay attention. Whether I'm dealing with a logit, if I'm dealing with a logit, whether I'm dealing with this guy, okay, which is a log of odd ratio, or I'm dealing with this guy, they involve log. Except that if I remove the log here and I take the exponentiation, I'm going to be talking about odd ratio. I'm going to be talking about odd ratio. Okay. But if I remove the log here, I'm going to be talking about maybe the count, the expected count. Does that make sense? Please pay attention to, and to remove the log from both, I will do exponentiation. Now, take a look at this. I know the customer will not, I'm sorry, the client will not understand the first one, because when you are interpreting and you say the log of something, they're like, what are you saying? They don't understand that. Then we exponentiate now. I know the client will understand this. When you exponentiate, that gives you 18.9. Then you can say, oh, that is the expected count of customers in the baseline group. That is the number of customers the store is expecting when every predator is zero. That makes sense in a way. Okay. Now that that is it. That is the baseline. But like I said, because when you're talking about region, it is not possible not to have housing in the region. It is not possible not to have somebody with income. It is not possible for all of that to be equal to zero. That is why we normally say, oh, that doesn't really make sense. But we still need to interpret the way we've been interpreting. Now, and of course, if you read more, this is the reason. It may be helpful to center our covariate, but this is not a big deal. We don't just consider intercept. We got reason why we still need to include intercept in our model, even if the interpretation associated with the intercept doesn't make sense. Okay, it's good. We have reason. We have a statistical reason. Okay, I need you to pay attention. You can see when I'm focusing on the estimate directly from R, I will be referring to the log expected. Does that make sense? You can see log expected or the log rate. But if I exponentiate, I will remove the log. Look at this. Can you see the difference? I exponentiate it at 1. Then I remove the log. Then I'm actually going to be saying that. Okay? If you can see that, I got 1 point. I said it's the rate ratio. Instead, initially I was talking about log rate. Now I've removed log with the exponentiation. Okay, so what I said is the rate ratio comparing district whose mean housing unit differ by 1 after adjusting for other covariates. You need to mention that after adjusting for other covariates. Does that make sense? Okay, now do you know if you take a look at what is happening here? 1 second. If you look at what is happening here, that is for 1 unit increase. What if I ask you 100 unit increase? Because it's if you want to talk about the way housing increases in a region, it may not just increase by 1. 1 is too small. I don't know if you are getting me. Now, what if I say, okay, by 100? Can you see that? By 100, before you exponentiate, you multiply by 100. If I say by 1,000, before you exponentiate, you multiply by 1,000. Now let's see this now. Okay, let's see the way this is going to be interpreted. When I do the exponentiation, before doing the exponentiation, I multiply by 100 because maybe the examiner said, okay, by do that with by 100, not just increase of 1. Okay, now we got 1.062 said is a rate ratio comparing the district whose mean housing unit differ by 100, not just differ by 1, differ by 100. Now there's something I need you to see. Another way we can put this, is to put it this way. Please pay attention. You know, here, that is 1.062. The 1.062, if you multiply that by 100, you're actually going to have maybe 106.2 or something. And what is the difference? 6.2%. Because it is over 100 by that margin. So we're going to say, keeping other factor constants, a 100 unit increase in housing will yield expected 6.2% increase in expected counts. Do you see the way I actually interpret that? Okay, and let me also say this. If I want to test how significance is a predator, then the name of the test is not going to be a t-test, but instead it's a z-test. There's something I needed to see. Here, can you see can you see that z value? Z. Okay? It is not a t-test, but for linear regression, it's a t-test. If you want to conduct the individual, if you want to investigate whether individual predator is significant or not. In a generalized linear model, I'm going to say that again. In a generalized linear model, okay, we use a z-test, not a t-test. Okay. And you know what? Whether a t-test or a z-test, it is still the same formula. It is still the standard error. It is still the estimate divided by standard error. Let's come here now. You got to see what I'm talking about. How do we get the z value here? Okay, it is the estimate here divided by the standard error. It's still the same in the t-test, but except that they have different names. Does that make sense? Okay. Now, that very z-test is what we call the word statistic. Word statistic. Okay. Okay. Now, I'm going to continue with the interpretation now. Okay. And I need you to pay attention. This is the second one, the one that has to do with income. Now, the beta 2, don't forget that you're actually going to have from a Poisson regression model, or the arrow output is in logarithmic scale. Now, this guy, to be the increase in the log expected log, consider expected or log rate ratio. You can call it either log expected or log rate ratio. Okay. Now, comparing these two whose mean income differ by $1, then after adjusting for other covariates. Okay. And that's exactly what I mean. If I want to remove the log, I will take exponentiation. Can you see that? Removing the log. I don't want to talk about log expected count. I don't want to talk about log ratio, but I want to talk about either expected count or rate. Okay, then I will take exponentiation. Now, after taking exponentiation, you see what I have? So after taking exponentiation, it's another thing. Another name we can call it relative rate. Okay, you can see relative rate. Okay, comparing region whose mean income differ by $1 adjusted for other covariates. But let me tell you this. No, $1 is too small. $1 unit increase is too small. What if you are they wanted to base your interpretation on $10,000? Don't forget, we are talking about region. Okay. Now, if I want to, what I'm going to do, I'm going to multiply before exponentiating. I'm actually going to multiply by 10,000, the beta by 10,000, and you see what I got. If you take a look at the value, that value is less than 1, right? Whenever you have a value, okay, that is less than 1, that will be a decrease. And that is not surprising, a decrease, because if you look at the beta 2 itself, let's go to the beta 2. The beta 2, oh my God, the beta 2 itself is negative. Do you see that? That is why that is not surprising. The beta 2, the income itself, is actually negative. Okay, so here, when you do multiply by 10,000, okay, you got a 0.889. Okay, if you multiply by 100, that will be less than 100. If you want to know the amount of change of the decrease, subtract that from 100. And that was why here we said, that would be around 11%. And that was why we said for a 10,000 change in average income, so for a 10,000 change in average income, we will predict 11% decrease in the rate of customer visiting the store. Okay, so that is what I mean. Now, another thing I want to talk about. You know, uh, it's just based on point estimate. I'm going to say that again. Our interpretation has actually be on point estimate. A point estimate could be wrong or right. A point estimate is a random variable, and that's why we need an uncertainty around that. Then we need interval estimate. Okay, now take a look at this. Right now, we may want to talk about the interval estimate of each coefficient. Okay, but let me tell you this. When I'm focusing on this one, then I'm only talking about the interval for the log expected count. Okay, take a look at that. So here, what I'm having here is just an interval estimate for the log expected count or the log rate ratio. Okay, now if I want to focus on the expected count, or I want to remove the log, I can also construct a confidence interval. Oh my God. If you take a look at this guy now, okay, that's an exponentiation. So what I'm going to do is whatever I got here, right? Then I will do it. I will do the exponentiation. When I do the exponentiation, then we can now talk about this guy. So that guy is going to make sense with that. Having describe something in an interval, describing something in an interval, you have incorporated uncertainty, which really makes sense. Okay, let me also tell you this. We can do confidence interval for situation where we don't also want a unit increase. Maybe the one that we want $10,000 increase. Take a look at that. We can do the confidence interval for the the for the expected count. So, which is what I have here. I remember the other time with the point estimate that we got was this is a point estimate. That guy could be wrong. All right. What is the corresponding interval estimate for this guy? Okay, the corresponding interval estimate for that guy is what you're seeing here. Can you see that? That is a corresponding interval estimate for that. Okay, so if you take a look at here, okay, this is just point estimate, point estimate. Okay, why the other guy here is the interval estimate. The interval estimate make more sense in research compared to the point estimate. Okay, now look at the way I'm going to interpret the interval estimate now. The other time, without any uncertainty, look at the interpretation for $10,000 increase or change. For a $10,000 change in average income, this 11% is a point estimate that could be too low, that could be too high, that is subject to variation. And we need to be able for us to say this. A very good interpretation is this guy here. Take a look at that. 95% confidence level for the relative rate of customer visiting the store is that for a $10,000 increase in the average income for the region. Take a look at that. Some of you may be wondering, why is it that there's going to be the number of customers that will be visiting will actually drop, even though there is an increase in income? The economists will explain that better, because at times when there's an increase in income, you may try to change your lane. Maybe you were using one type of car before. Oh, I want to use the latest car. So money at times, somebody will say money or weight at times. Uh, that is that for Poisson regression. I'm confirming to you 100% there will be Poisson regression module in the final. Of course, you've all seen what is it called? You've all seen the final exam practice questions. I want to go into another, which is going to be the last in the semester, but it's very, very important, and it's kind of it's new, in in research. So I want to introduce you to beta regression model, crucial.